right. Hello, everyone. Glad to see you all, those that are here. We're getting empty. We're probably going to get through most of the PowerPoint today. I don't know. I'm just like feeling it out because we only have so much to do, and it's one of those, once we get through it, it's done.
You could cancel class for Tuesday, next Tuesday, have the review.
Have the review, yeah. Y'all are paying me. I can't cancel it, but
I think you could.
I'll be here. We'll do the review next Tuesday. Now, I say that, a couple things to point out. This is working. It's just very weak. I posted the test, so you may or may not have noticed that. No idea. I doubt it notifies you. If y'all go into test 2, if you want to look at the answers, they're all there. The multiple choice, there's not really much to point out there because, again, there wasn't any one question that less than 40% of people got right. This one, so I've already graded my free responses. I think Angelina's done with hers as well. So tomorrow I should hopefully have your all's free response grades posted.
How were they?
Yeah, I think they were pretty good. Mine were pretty good. Angelina, how are yours?
Yeah, pretty good.
Pretty good. Yeah, pretty good. This problem, I want to point out the most common mistakes, and specifically in the free response. This one, the most common mistake was people treating this bottom wire as an infinite wire. Saw that again and again and again and again. So that was super common. You didn't miss a ton of points for that, but just, be careful. This one, my experience was people are pretty bad at series and parallel. That was surprising. On the final, there will be a question where it's a bunch of resistors and it will say combine them into one resistor. There will be a circuit that's a bunch of capacitors and it'll say turn it into one capacitor. Series and parallel is just one of those things. This worked out thing has 3 different examples, and it also, I drew the circuit each time so you can kind of see the steps. But yeah, I saw some notorious, people really want these to be in parallel. They're not. They start together. They definitely do not end together. These are not connected at the ends. There's these big resistors in the way. You have to combine these first. And then you can do the parallel. Yeah, people really, when they saw a junction, they really wanted to say that was parallel. There needs to be a junction on both sides of the resistor, is one way to think about it. This one, largely good, though the version I had, something I saw, and this class is my lecture class. Make sure you all can do these integrals. This integral specifically, about maybe 40% of people couldn't solve this integral correctly. And this is, in my opinion, a simple integral. This is a skill. You all need to be able to do integrals. You're going to see them in your future classes, soapbox, all that jazz. But I was kind of surprised to see that. Make sure you all can do these kind of integrals. There's the 4 different ones, yada, yada. That's just more of less this class and more of your future classes. This is something, doing the integral was supposed to be the easy step, in my opinion. So if you messed it up, that's okay. You learn, you move on, but that is something maybe brush up on. This one, you need to recognize this was amplitude and then to divide it by that. The most common mistakes I saw here were not putting the whole thing and saying that was the amplitude, or here I said this is angular frequency. Some people put it as F instead of W. So that sometimes happened. And this one was also one that, I don't know, these are all kind of worthwhile to look through. If there's one you didn't know how to do, you should probably look over it just to make sure you know how to do it in case anything like it shows up in the future. This problem was actually pretty straightforward. These 2 wires just act like an infinite wire. And Ampere's law and yada, yada, yada. All right, cool. That's that. But for studying wise, y'all I'm not making any new resource. Okay, I will make a very small review on electromagnetic waves, but I'm not going to make a new review for test 1 stuff. I'm not going to make a new review for test 2 stuff. You all have a ton of practice problems now to pull from. You have the problem sets, you have the quizzes, you have both of the old tests, you have test 1 review, test 2 review. So I say this not to this is not me yelling at you. This is just saying, hey, there's a lot of stuff. Make sure you're aware of the stuff. Use it, all that jazz.
Will we be able to post all the iClickers?
I will do that, yes. That's a great question. I will make a PowerPoint slide with all the iClickers combined together. That'll be pretty straightforward. I'm just going to take the test 1 and test 2 one and copy and paste, and then take the new ones and tack it to that, and that'll take me like 10 minutes. Less than that even. So I will post something for the final, but there's not going to be like a final. I mean, okay, look, you see here there's a final review. This is old. This is from my like 2054 class, so it's not actually up to date. In fact, I should probably delete these because they're just not, they're not very useful. So I'm going to delete them, and this is not me taking away materials. These just aren't very good materials. Like, I don't recommend actually referencing these. These are from older classes, and I haven't updated them. So I'm not trying to be mean and, like, deleting useful stuff. It's just not useful. So I don't want you to be confused and think it is useful. All right. Cool. Joke of the day.
Hello.
Yeah, the mic's not.
Hello. To the person who stole my Microsoft Office license, I'm going to find you. You have my word.
Yeah, it's good. All right. I think that's it. I've answered this question. I'll answer like the most common questions. I get them again and again, so I'll just keep answering them because clearly they're important. The final is going to be, currently the plan is 40 multiple choice questions. We have about 10 to 11 weeks of material, depending on how you kind of slice it. It says 11, but some of these are kind of short. So roughly each of these weeks will have roughly 4 questions in them. Again, I say roughly because, for example, this electromagnetic waves we're actually covering for a week and a half. So that one will have 6 questions. So there'll be 6 questions on the final for electromagnetic waves, and then the rest is kind of divvied up based on how the time we spent. This is the current plan. I've been making the tests. I'm at about 30 questions or so now. Getting there, and I'll polish it up and double check for typos and all the fun things. You get a 5x8 note card in the test. I will bring 5x8 note cards this Thursday. I'll bring 5x8 note cards this coming Tuesday. What's the last thing? The test will be in this room. I'll just go ahead and show you all this. I mentioned this before, but if you ever want to know when your exams are, just Google UCF final exams. First link that pops up, you pick your meeting pattern. So ours is Tuesday, Thursday, 2 p.m. to 4:50. Nope, 4:50. Great, there we are. Something I want to point out is my other exam ends at 12:50, 2 floors down from here. So I'm going to be booking it back up here, but normally I try to get to exams early, but I probably won't be able to get here early. So anywho, all that to say, bear with me on that. I didn't make the rules, but so it'll be in this room, just like every test we've ever done. Great. And we will have a lab this Thursday. The plan for the lab this Thursday, it's going to probably look a little different than our other ones. It's going to be optic. It's going to be light related. Instead of previous labs where I said, hey, do this, do this, do this. This lab's actually going to be, hey, figure this out. Here's the equipment. And then give you a bunch of a rubric that we're not going to really like. So all the other people do this thing called a lab final. I'm basically going to give you that lab final, but we're not going to grade it as rigorously. All right. You're going to, basically the goal of the lab will be, hey, here's a material using light and how light bends determine what the material is.
It'll be weighted same as every other lab.
Yeah, it'll be weighted the same as every other lab. But just to give you all there will be a lab, and that's the current plan. It'll be interesting. It'll be fun. All right, cool. Waves. Started talking about waves last time. Specifically, no, we did lots of waves. We talked about what the wave function, and it was this fancy looking thing that might look intimidating, but it's just a wave that's moving. That's why it's got that VT term. And we derived it. It was great. We had so much fun. And then we said light is a wave. Why? Because of experiments and because of theory and because of all the things. And so we get the equation somewhere. There it is. It's the same exact equation, but now we've got E's instead of amplitude. We have C's instead of V's. So to write the original on here, like the wave equation from before, just so you can compare the two. This is a wave that's traveling in the x direction. It's the amplitude times sine of 2 pi over lambda times x minus plus vt. There's a plus a phase angle, but I ignored it in this one. And look, they look the same. Yay. This E naught and this B naught are the amplitude of the waves. And that's where we left off. Light is a wave. There it is. And we talked about how you make these waves by making charges wiggle and showed you an animation. It was a fun time. And that's probably something, I'm not going to test you on how light is made and stuff like that, but I think it is really important for you all to understand what wireless signals are. Specifically, this is what a wireless signal is. Every Wi-Fi, phone signal, Bluetooth, it's just these waves. Now, they do some fancy things with these waves, do a bunch of frequencies together, all that kind of jazz. But what I really think is important for you all to understand, I showed this in the animation last time, is that what do these waves transmit? They don't carry material. They don't take material from one location to another. It's not like a physical thing moving. What do these waves carry? Information. These waves carry information. And that information takes time to travel. So I showed you all, wasn't this one, that when we wiggle this, we get a field. And this field travels. So like when I wiggled it one time, this information takes time to make it to the receiver. And then when it does, this thing wiggled. You couldn't tell, but it did. It's not instant. There is a time it takes. And the example I like to reference a lot is the sun. When you are looking at the sun, you are seeing what it looked like 8 minutes ago. If you go outside and you stare at the sun for some terrible reason, you are not seeing the sun right now. You are seeing the sun 8 minutes ago. If you want to communicate with a rover, if you want to communicate with something that's on another planet, there's a reason that this is so challenging, and one of it is that you can't control it. Say you're trying to land a rocket on Mars, and say you're trying to control it by hand. If you're like, oh my gosh, I'm getting really close to that rock. Yeah, you hit that rock 30 minutes ago. You already hit it. It already happened. Your rocket's already blown up. You can't control things by hand over, like, light is fast, but the universe is bigger. And when you get to other planets and things like that, you can only transmit information so quick. And so it's a really important idea that you all understand, just as scientists, is this idea that information takes time to travel. When I hit that light switch, what I'm effectively doing is sending an electric field. In some ways, you can think of it like a wave. These lights do not turn on instantly. It's effectively instant because the distance is so short and it's at the speed of light. But when you flip a switch, it's an electric field traveling through that, updating throughout that wire, and it takes time. It's so quick that you can't tell. But when we get to large distances, you can. So, all that to say, it's a really, really important idea that when we call these waves, you're not transmitting any information, or you're not transmitting any physical stuff. These fields are just updating in space. You can't see these fields. They're not physical things. The only way that we know these fields exist is if I put something in them, it experiences a force. It's fields are a weird idea, but it's how we describe this information being transmitted, even though there's no physical object that's being transmitted. It's a very, I don't know what to call it. It's a weird thing. It's an idea. Anyway. All right. So great. We got these. Yay. This next slide is going to look intimidating, but you all can do this. It's not that complicated. And I say that sincerely. Here is a magnetic field. Here's a wave. I have my electric field, which oscillates in the Y. Means it wiggles up and down, for example. And this is always a fun thing to draw. So I'm going to draw like my coordinate axis. So this wave is traveling. See how good of a job I can do conveying this. This is X, this is Y, this is Z. My wave is traveling in the X direction. That's why these are both functions of X. That's the direction we're moving. My electric field is oscillating in the Y direction, meaning my electric field is doing this. It's wiggling back and forth along the Y axis. My magnetic field is oscillating back and forth in the Z axis. And that's even more of a pain to draw. It's oscillating this way. These fields oscillate perpendicular to each other. All right, not something I'm going to really test you on, but it is something that I just want to mention here. So great, I got a magnetic field in the z direction. Let's call that up, down. We got an electric field in the y direction. That's left, right. They're both traveling in the x. This is a statement I told you before. I said that the partial derivative of the b with respect to t equals the partial derivative of the e with respect to x. Where did that come from? I basically pulled it out of thin air because the derivation is a pain in the butt to show. But it does come from Maxwell's equations, so this is one of those few rare cases where I just say, trust me. You can look it up if you want to. But this next part you can derive. I have these two equations. This is the same field. They're coupled. Anytime you have an electric field, you have a magnetic field when it comes to these. You always have both. So this relationship says if I take the partial derivative of the b1, it equals the partial derivative of the x1. I want you all to go ahead and do that. Set up that expression and see how E naught and B naught compare. You may or may not have seen partial derivatives. They're really easy. The partial derivative with respect to t means take the derivative with respect to t. Everything else is a constant. Partial derivative with respect to x means take the derivative with respect to x. Everything else is a constant. So try it out. And find the relationship between B and E using this. And this will be a useful relationship for us to know. You're going to deriving it from this equation that I just said, trust me. And just to make our life a little easier, let's just say these fields are traveling. Let's make them travel to the left just to avoid any negative signs. It doesn't matter the order of direction, but we're just going to do this. Here's a field traveling to the left because it's a plus sign. Traveling in the negative x direction. You're definitely going to want to write this down. Doing this in your head just seems like a terrible decision. This is not a do in your head problem. Oh, I didn't send it. Write it down. Doing stuff in your head is more work. It is lazier to write things down. Be lazy. Write things down. Wait, partial x. I did the partial. How did you know the name with the partial symbol? Does it have a name? I don't know the. So. I don't know the name.
I think I've always heard of partial.
Yeah, that's that.
Yeah.
You go to that restaurant, should be. Basically. Oh, you were just equal to.
You have to decide both.
I don't know why I just never think of like the deal with the city. Should we gamble because it's one thing.
Have you heard if there's like a name? You just ask. I don't think I can it's called partial.
Yeah.
I've heard some people say Bell, but that's already like taken.
That's the thing. Is, like I'm pretty used to Dell, but that like I prefer like keeping Dell than upside down Dell. Like,
Yeah, I think it's
All right, give y'all about 20 more seconds. Very important. This is a derivative you all should be able to do. If not, it's good practice. Either of you want to do it?
fingers crossed.
Go through and be like, it's fun to do these things that are simple and easy.
Yeah.
Exactly here, yeah.
No, you
got it.
You'll be fine. The only thing you have to be careful of is remember that 2 pi related goes with both terms.
yeah.
You got this.
Oh, you're right.
All right. Let's take these derivatives.
Oh, you probably want to close it.
Oh yeah. And that's 3, 2, 1. Hopefully, you picked an answer. All right. So, starting with the left side of that equation, we're trying to take the partial derivative in terms of t of b naught sine 2 pi over lambda x plus ct. So, we know that b naught is a constant. We can just pull that out as it is. And I like to distribute the 2 pi over lambda because that makes it easier for me to read that equation. So that's sine 2 pi over lambda x plus 2 pi over lambda ct. And so we're taking the partial derivative of that. Now the x term is we're not caring about that when we take the derivative. We're only looking at this t term, but that's within the sign, so that we use our chain rule. And that gives us b naught. So sine's derivative is cosine. So we keep the inside all the same. And then the chain rule part of things is next to our t, we have 2 pi over lambda times c. So we just multiply that by the whole term. And that's our left side. Over to the right, in this case, we can pull out E naught as our constant, and I'm just repeating what I did with distributing that 2 pi over lambda. All right. And once again, derivative of sine is cosine. And using our chain rule, which I've kind of run out of room, so let's see if I can squeeze things over.
I got the whole thing.
Oh, should I?
You can shrink it all.
That kind of worked.
However you fit it.
And so this time, the coefficient of x is just 2 pi over lambda. Yeah. And so we want to set our two terms equal to one another. And we can recognize, I'll use a different color, that the cosines cancel out all of that stuff that's inside. And so you're left with b naught 2 pi over lambda c is equal to e naught 2 pi over lambda. And so those terms will also cancel out, and you end up with b naught times c equals e naught, which is the same as b naught is equal to e naught over c. And that's this one.
Yay! Yeah. So you might be like, what was the point of all this? All of this was to prove this statement. The magnetic. Oh, and I really want to point this out because I always get this question. This B naught is the amplitude of the magnetic field. It is the maximum value that the magnetic field wave is. This E naught is the amplitude of E. It is the maximum value of E. So if I go way back to the beginning of this PowerPoint where I showed you a pretty little picture, and this is the electric field and magnetic field, it's much better than I could draw. When I say E naught, I am referring to this maximum value. When I am saying B naught, I am referring to the maximum value. Why? Because it's in front of the term. It's in front of the sign. That is the amplitude. That is what amplitude is. So, again, just making sure we're cool with waves. And what this says is, read it. It says the magnetic field amplitude is the electric field amplitude divided by C. C is a big number. C is, we've actually already talked about this. C equals 3e to the 8. Let's actually write that down. Let's write that out. Because we haven't seen that yet, and sometimes in a scientific notation we lose perspective. It's 300 million. If I divide any number by 300 million, I get a small number. So this says that the magnetic field is much smaller than the electric field. And we've kind of mentioned that in this class. It's really hard to make a big magnetic field. It just is. If you get I think the strongest magnetic field we can make is about 10, 12 Tesla. They can make hundreds of Tesla, but only in a really short period of time. For fun facts. All right, so great. There's another relationship for C. See, we derived last class that's 1 over the square root of epsilon naught mu naught. We're also seeing that it's the ratio of the electric field and magnetic field, which is kind of cool. And this is just kind of a weird thing. This is the speed of light. Functionally, it's how fast the light's going. But what's weird is that it's equal to these other things that have nothing to do with how fast it's going. It's related to the amplitude of the wave. That's kind of weird. It's related to epsilon naught and mu naught. So I don't know. It's just kind of a weird thing that does emerge. And to clarify here, you can't just be like, oh, I want to make it faster. I'm just going to make the amplitudes bigger. No, that's not how it works. You can't just crank because they'll cancel each other out. They're coupled together. If you make the electric field bigger, it in turn will make the magnetic field bigger. And so you always get the same ratio. All right, great. Let's see if this makes sense. Use it. We're going to assume this is in base units. We'll just kind of assume that. It would have been better if I'd said otherwise. Here's an electric field. What's the value of B naught? You'll notice that half of the problem set 3 is, can you read the wave equation? Can you make sense of it and build it and all that jazz? They all come here. Yeah.
No,
Good guess. That would be very problematic. The fastest we could be. The fastest we could go is 10 nanometers.
you walking around this.
No, maybe that is but time's all relative, right?
No, it's not.
The E is 5, right?
Yeah.
And B is equal to 1 over C.
Did I do that backwards?
So,
Multiply the C by the C.
I'm going to check this to make sure. Which should be bigger? The E field or the S field?
Oh, is that like moving or something?
B fields are hard.
Shifted over time.
What's giving them a problem here?
Oh, that's a problem.
Yeah, no, you're good. Look, you will make those no matter how long you're doing this. You're gonna multiplying instead of dividing, missing a factor of 2, forgetting to square something, losing a negative sign. Classic. All right, 20 more seconds.
What'd you say the strongest continuous magnetic field we made with?
I pulled that
I
out
just
of my head.
looked it up. It's 45.
Huh?
45 Tesla. Apparently.
Oh, really?
Tallahassee.
Okay. No, I'm sure that's right.
Yeah.
I said 12, but
That's strong.
that is very strong. No, I know that Tallahassee FSU.
It's the National High Magnetic Field Laboratory.
Yeah.
Apparently.
All right, I'll update it. I appreciate it because I forgot. That was like.
The strongest pulsed one is 100 Tesla.
All right, in 5, 4, 3, 2, 1. All right, so we can look at the answers here, and there's only one answer that's realistic. The magnetic field is much smaller than the electric field. There's only one answer here that's much smaller. So, just by like logic alone, understanding the concepts. Now, if you want to see the math, this is the expression that we're going to be using. We'll always write it kind of in terms of C. That's the way it's given on the formula sheet. So if you want B naught, get it by itself. That's going to equal E naught divided by C, which is going to equal 5 divided by 3e to the 8. I know my 5s look like S's. It's a problem. I haven't figured out a solution to it. There you go. What a grand time. Tyler fact-checked me, which I do appreciate. So, Tyler, here, I'll let him share. On the statement I made previously.
So currently the strongest continuous magnetic field is 45 Tesla, and it was made in a laboratory in Tallahassee.
FSU's got a big lab on magnetic fields. They're actually, leading experts. That's one of the things they do there. And then the other thing he found is like the strongest quick pulse was about 100 Tesla. 100's not like that big of a number compared to a lot of the numbers we work with. That's why I was telling you, it's like, it just is what it is. Sometimes we define units in some ways. Numbers are arbitrary, right? Well, I say that. I guess these are related by 3 times 10 to the 8. So if we made the B fields bigger, then the E fields would be like ginormous. So one of these either's got to be big or the other's got to be small. We're stuck. Fun. Look, all the fun facts. Speed of light is the new standard that all units are being based off of. You're like, what the heck is he talking about? When I tell you a kilogram, there's an important question that you may have thought about, maybe haven't. Who decides what a kilogram is? You need a reference. This is something you probably don't think about too much, but especially engineering majors, you all better be, standards are very important. Having accurate measuring tools and being confident that when I say my ruler, so this is another fun fact. You know the slide tape measures that you all get? If you bought like 5 from 5 different companies and you pulled them out a bunch, they'd be off by like an inch or so. It's surprising how it's really hard to make things that are standardized. So back to the original topic. 1 kilogram used to be defined by a sphere of some metal. I don't know if it was tungsten or I don't remember. That was like in a sealed jar over somewhere in Europe. And every now and then they periodically check it. Fun fact, it was steadily losing atoms. Why? Because that's everything. Everything outgases. Entropy is always increasing. Everything's evaporating. Just like water, when you leave it out, it eventually turns into a gas, even though it's not boiling. Every material does that, which is wild. If you have a piece of metal, the metal ions a little bit. Anyway, the kilogram was decreasing. That's not a very good standard. You want your standard to not change. That's why it's called the standard. It doesn't change. The speed of light is one of those such standards. Our current understanding is that the speed of light in the universe hasn't changed. We're hoping that's the case. That'd be kind of weird if it did. And so currently a meter is defined by how far light travels in some number of seconds. And then you're like, but wait, how do we define seconds? Seconds are defined by how many times how long it takes a cesium atom to vibrate a certain amount of times. These cesium atoms vibrate periodically, like a wave, and it's very, very consistent. And so the time it takes for them, let's actually just Google this real quick. I want to give you all the right number. How is a second defined? It's going to be a cesium atom. All right. The duration of 9,192,631,770 oscillations. Oh, no, it's different. Yeah, okay. Correspondence between... let's just say it's oscillating. It's kind of sort of oscillating. It's I think maybe even an electron like jumping between levels. Yeah, hyperfine splitting gets into quantum mechanics. Don't worry about it. But it's defined by you count something. They literally count something, and that gives us a second. And then speed of light is a constant in the universe, and then they go from there. So cool stuff. Things you don't think about. All right, ready to chat about this? Okay. I semi-regret giving this problem because it's so hard to draw a picture for this, but it's fine. We're going to do it anyway. It's not a hard problem, but drawing a picture to understand one piece of it is a little funky. All right, so I'm going to do something a little, just to make my life easier. Here is my YZ plane, and my x-axis is going to come out of the board. It's just going to be a pain in the butt to draw this picture otherwise. So this wave is traveling in the x direction. I have a plane wave with a frequency of 600 times 10 to the 12 hertz. That is the frequency of green light. That is like that green light. That's its wavelength. No, not wavelength, frequency. It's in the x direction. So imagine it's coming out of the board. And the electric field has an amplitude of 42.42. Now the next words, there's going to be some words here that are going to get referenced, but we're not going to worry about too much. If the wave is linearly polarized, such that the electric field oscillates at a 45-degree angle above the y-axis, what are the equations for the components of E and B? So this is where I needed the picture to draw this. When I say this field is linearly polarized, it just means it's oscillating in one direction. Technically, light could oscillate this way, or this way, or this way, or this way. Each of these could be like oscillations. It's only oscillating one way. It's wiggling up and down one way. Which way is it wiggling up and down? My electric field is doing this. My electric field wiggles up to the right, then down to the left, and up to the right, and down to the left. The electric field doesn't always need to be pointed up, down. It could be in any orientation. We call this the polarization of that light. All right, the magnetic field oscillates 45 degrees to that. All right, so this is my electric field. This is my magnetic field. My magnetic field should be much smaller, but whatever. It's arbitrary units. And these are oscillating out of the board. So just to remind you all what this thing looks like. This pretty picture I'm going to keep referencing because it's better than anything I could draw. So imagine this rotated coming out of the board. That's the visualization I want you all to have. That picture on the right coming out of the board, but it's rotated. Okay? That's the idea. Okay. This is really going to only matter for one small thing. I'm not going to actually give a problem like this where they're not lined up with the axis because it's such a pain to explain. All right. What I do want you all to do, make the equations. This you can do. For now, just make the electric field equation. We will have to break it into components, but for now, E as a function of x comma t equals, I want you all to try to build it. Don't worry that it's at an angle right now. Pretend like it doesn't say that. Just don't worry about that right now. We will care about it in just a tiny bit, but you all can build the wave equations. Amplitude, sine, 2 pi over lambda, x plus minus, minus plus. You got this. This problem is easier than it seems. Just build the wave equation. Go back, get the template for the wave equation, and then plug in the pieces. You will have to do a little bit of math. Very little. what I'm looking for when I walk around and looking at papers, I'm seeing if you wrote the template. Write the general expression for what an electric field looks like, what the electric wave looks like. Start there. If you don't have that template, you're gonna have a hard time. And it's in the formula sheet if you're not sure where it is in the slides.
Yeah. From the electromagnetic, yeah. Yeah, I did this formula and then used the equations for K. I saw for wavelength first, and I just used these to write it up. But I think so. The x components are 0, right? If EY is going like this and B is this, then BY would be negative. I'm keeping it in like variables, right? It's just the Y is the one that's flipped, but the Z is matched, right? Like it's not both are flipped, because then it would just be the same as the E. It's just a reflection across the Z-axis, so I think you need minus the Y. Oh man, I'm thinking about linear algebra now. Standard basis.
There it is.
That's what you usually break.
Otherwise, yeah. So now we did it. And then the rest of the stuff. Then now we
I got this.
But
You just divide by 2 squares.
that's actually pretty simple.
To get the
I have a question.
Yeah.
Since for the components, like if I wrote it the B9 in terms of
Yeah, perfect. We're gonna end up having to do this.
why would he
It does end up being negative.
right?
Yeah, which is
And would you define out of the pages negative too for the direction? For positive X?
yes.
Okay.
Yeah. So these end up both being positive. Yes, you are completely correct. This one's
Okay.
negative, and then this one's because it starts going that way.
Right.
Just- I'm not gonna worry about that. I'm not gonna actually test them on
Yeah.
this cross product thing. Complete pointing vectors.
Yeah, it's like
I had to pick and choose. All right, so this is the original form. If you didn't have this, you're gonna have a hard time solving it. I mean, you could probably maybe do it. I don't know. So that's like the general wave equation. Now, in this case, this is not necessarily the one on your formula sheet. But you know what? Actually, let me just put the general one on the formula sheet. because that is the one that you'd have on a test, so it's good to kind of use. So the general form of a wave is given by the amplitude times sine of 2 pi over lambda times x minus plus vt plus a phase shift. That's the one that's kind of on the formula sheet. So now all we need to do is, if we want to do the electric field, we're going to replace amplitude with the electric field amplitude, just to kind of quote-unquote derive this. We're going to replace v with the speed of light, and great. It just comes from that fairly naturally. All right, so now you just put in the numbers. What's the amplitude of the electric field? 42.42 times sine of 2 pi over, what does this little wiggly waggly, it's called lambda, what does that thing represent? What variable? It is wavelength. Something that I decided today, it kind of looks like a wave, like an ocean wave. So maybe that helps you remember that it's wavelength. Is it? I don't know. It's a wave, and you could measure how big it is. Whatever. If it helps, it helps, right? It's not stupid if it works.
Okay.
So that's wavelength. Now, the problem is I didn't give you wavelength in this problem. Wavelength is exactly measured in the units that the name says. Length, meters. Nothing in this problem says meters. What is given in this problem? Frequency. It says the word frequency. Also says hertz after it. So, then we just remember the equation that's 3 slides above this. Well, it's written a little differently. V equals F times lambda. In our case, it's the speed of light equals F times lambda. And so rearrange this and you get C over lambda equals that's not what I want. I want wavelength. Wavelength equals C over, what I wrote wasn't wrong, it just wasn't useful. All right, so great, that's my wavelength. So my wavelength is going to equal 3e to the 8 divided by 600. I'm going to do this because I want to. I'm going to make my life easier to do it in my head. 600 times 10 to the 12 is the same as 6e to the 14. You just go up by a couple orders of magnitude. 8 minus 14 is 6, negative 6. 3 divided by 6 is 1/2. So I get 1/2 times 10 to the negative 6. You could also plug in the calculator and get that. And this comes out to 0.5 times 10 to the minus 6 or 5e to the minus 7. And that's the wavelength of green light. It's 500 nanometers. You do not need to be able to do this kind of stuff in your head, but it's a valuable skill to be able to work with scientific, remembering you can subtract them and add them and things like that. Give you a good order of magnitude. Which way is this wave moving? Positive x or negative x? Positive. So should I subtract it or add it? Great. Subtract. And there is no phase shift, and great, that's good enough. I don't need you. If you really want, I guess you could plug in C. We just leave C as C. And I guess in astronomy, they just make C1 or something or silly like that. Sometimes when you're working with a variable so often, you just make it 1. Whatever. Okay, now, before we get to the magnetic field, we're going to do something here. Again, I'm not going to do this in the test, but it's semi-worthwhile to show. Look at my picture. It's a vector. If I want to describe this, it's useful to break it into components. So, for example, I could find the electric field in the y component. How do I do that? I make a triangle. These are vectors. I can break them into components. How do I get the y component of that triangle? What am I going to take my original vector? What am I going to multiply it by? Sine of 45. Why? Because this angle is 45. Because it says so in the problem. So if y'all want you'll notice that the answers are written this way. That the answers aren't written as the net vector, but are rather written as the components. So the E field in the y direction is 42.4 times sine of 2 pi over 5. It's the same exact expression. It's kind of a pain to write again, but whatever. Times sine of 45, which is square root of 2 over 2. I'm just going to leave it like that for funsies. And that's in the j hat direction. That's y. If I want the z component. Oh, I did bad here. No one corrected me. The y, was it the adjacent or the opposite? Adjacent. What do we do for adjacent? That's all right though. We learned. Look, I trusted it too. All right. The z component is going to be the opposite. So this is ez, this is ey. These are vectors. This field is just a field of vectors. Or this wave is a wave of vectors. When we get a positive e, it means an e that points up, quote unquote. It points along the positive version of that. Okay. And this is k hat, because that's in the z direction. Fantastic. There's the electric field one. The magnetic field is going to be the same exact equation. Only one thing will be... Okay, I guess there's technically a couple things different. I'm just going to kind of write these briefly. I'm going to steal my pictures because they're useful. I will give you all problems where I say, hey, a wave's got this frequency, a wave's got this amplitude, write the equation. I'm not going to give you ones that's like shifted by an angle. Just to assuage any fears you might have. So if I want the B field, B as a function of x comma t equals B naught sine of, how quickly can I write this and it still be legible? X minus plus ct. Oh my gosh, it's the same expression. How do I get B naught? Tell me. B naught equals E naught over C. Why? Because of the reasons we said before. Remember, C equals... I'll write it out. I'll be kind. C equals E naught over B naught. Therefore, B naught equals E naught over C naught. B naught equals, 42.42 divided by C. I'm not going to solve that. It's just going to exist like that. 42.42 over C times sine of 2 pi over lambda times x minus plus ct. All right, we need to break this into components, and here's where things get a tiny bit funky. It's not bad. It's not anything crazy. So as the electric field wiggles up to the right, the magnetic field is going to wiggle up to the left. Notice, okay, so let's break this into components. So this, make it a triangle. And when we make this triangle, hopefully we're going to remember something about our vectors. Let's do the y component first. Which way does this y component point? Does it point left or does it point right? What happens when things point left? What do we need to put in front of it to denote that it's left? So this is a little subtle thing. Again, I'm not going to do this to you on a test, but there's a negative sign here because it's to the left. Sine of 2 pi over 5e to the minus 7 minus c times t times cosine of 45. And I forgot some things. X minus ct times cosine of 45. The z component points up, so we don't have to worry. No negative there. Positive 42.42 over c times sine of 2 pi. This is like the worst case scenario problem. Again, I'm not going to give one of this level, but you better be able to build these equations. I'm not worried about breaking them into components. I am worried about, could you do that first step that we did? Can you find this electric field magnitude? Can you find this magnetic field magnitude? I really care about that. So, this way you don't get too scared by these things. All right. And at this point, we have done the wavy stuff. And we're kind of getting to the next three things. The next thing I'm going to teach you is the energy carried by a wave, because that's fairly relevant. We're going to use the word intensity. It's going to be the energy per unit area. It's basically how strong your signal is one way to kind of make it engineering-y. We're then going to learn about how light behaves in different materials, and that'll kind of be it. And I say that'll kind of be it. We got like 20 more slides. So we'll see how much we get through today without... It's not too bad, though. Before I get to that, though, there's something... I'm not going to test you on this because I don't even know what the problems would look like. They'd be a little bit too trivial. waves do something called constructive and destructive interference. I needed to put a slide on this because if I didn't, I'm not doing a service to waves. So let me explain this picture down here. This picture, great picture. I'm going to eventually pause it. Let's see. Oh, I did too good of a job. All right. What's going on in this picture is I got two waves. I got a blue wave and a green wave. What's happening here, and this is true of all waves, when you have multiple waves, what ends up happening is the waves combine together. The high points add together. Think of when it's up, it's positive, and when it's down, it's negative. It's vector addition. So, for example, at this point, let's just pick a random spot. Make this a little thinner. At this point, my B field is this big, and my green field is this big. So how big is my red field? Both of them added together, right? They add together. Now, this is called constructive interference. When the waves line up, the high points add together. Yay, you get a bigger wave. Now, if I keep playing this thing, notice that this wave, one of these waves is traveling to the right and one of these waves is traveling to the left. And this red wave constantly is changing based on their location. So this is when we get like really good constructive interference. We get a really big wave. This is pure destructive interference. So what's going on here? When my blue wave is pointed up at the exact same point, my green wave is pointed down. So what's +1 - 1? It's 0. So my red wave is flat. A really great application of this, if you're like, so what? This is how noise canceling headphones work. So this is a cool application of this. Noise canceling headphones, they're a big thing now. Most people have them. My high schoolers, my gosh, they all had AirPods. And then anyhow, that's inside. They'd lose them all the time. And I'm like, that's $100. They would just lose them all the time. Leave them in the classroom, whatever. They have noise canceling. How do you cancel noise? By making more noise. That's the crazy idea with noise canceling headphones. Noise canceling headphones don't work by putting a bunch of you're not just shoving your fingers in your ear so that the sound can't get to it. What a noise canceling headphone does is it has a microphone and it's picking up all the outside noise, all of it. Then what it does is it flips that wave. It picks up that signal, flips it, and then plays that noise back. And so you get a wave you got the sound from the outside and you got a completely inverted sound. It sounds identical. If you played just the sound that if you couldn't hear the outside noise and you could just hear what it was playing back to you, it would sound like the outside noise. But crazily, they're flipped. And when both of them are happening at the same time, they cancel each other out. It's a really weird thing. An inverted wave sounds identical to the original version. If these were sound waves, the blue and the green wave would sound the same, which is wild. It's kind of weird. But when they're played at the same time, if this was the case and they were perfectly on top of each other, they cancel each other out. It's cool stuff. So yeah, constructive and destructive interference, that's what results in these fringe patterns. I think I showed you all this. You can do this in a pond. So if you have two sources of waves and you're like, how could I do this? If you just get two balls and you have them in water and you kind of oscillate them up and down, you will actually see this pattern emerge, which is kind of cool. It's a really cool kind of experiment. And you get these little fuzzy areas. That's where destructive interference is happening. And in between them, we get some constructive interference. If I do the 3D view of it, you can kind of sort of see it. So if y'all look along this line, it's perfectly flat because it's purely destructively interfering. It's just how the math ends up working out. That at that line, the waves where one is up, the other is down. They are perfectly 90 degrees out of sync of each other. And when they're perfectly in sync with each other, you get a bigger wave. And yeah, it's cool stuff. Another application of this constructive and destructive interference is this is something they have to do in every sound engineers have to take this into account. So when they're designing, anytime there's a concert or anytime there's a music hall or things like that, they have to actually locate where these dead spots are. When they set up their speakers, these speakers are acting like point sources, and there will actually be places in the crowd where the noise completely like cancels itself out due to the two being out of phase of each other. So this is something they have to design for when they're building concert halls and determining where to put speakers, because this will happen, which is cool. Anyway, it matters when it comes to waves. That's my big thing here. I'm not going to test you on this, but great. Okay, waves carry energy. This energy varies with time and location. The closer you are, more energy. More time, you're going to get more energy. This is obvious. You all go outside, eventually you get sunburned. Why? Because you received more energy. You got bombarded with electromagnetic waves. It's quite useful to measure how strong this energy is. All sorts of applications. If you're sending a wireless signal, you sure would like to know how strong that signal is going to be at the place where you're receiving it. Is it strong enough to even pick up? It might not be. And then you need to output more signal. Okay, so this is the general, this is not anything new, this is not derived, this is a definition. Intensity is the amount of energy you get per second per area. It's not energy per area. It's the amount of energy per second per area. The unit of watts, the unit of power, is joules per second. Power is watts. Watts is joules per second. So, written another way, this is joules per second dot, there's a meter squared there on the bottom too. So, it's a useful thing to understand. On the bottom is a couple definitions that the first one you definitely should have seen before. It's a definition of power. It's how much energy per second. U is potential energy. T is time, energy per second. The second term is how you average anything over time. That is a definition of an average over time. You take a derivative, you take an integral. I don't know why there's a 1 here. Don't worry about that. Oh, it's gone. All right. From 0 to t, and then you divide by t. Get all the energy and divide it by time, and that's going to give you the average power. Those are just definitions on the bottom. They're not necessarily new. But we need to find this. And now my big question is, how much do I go into the derivation? I am going to go through it very quickly. The next 6 slides are just deriving the intensity. There's some cool stuff in there. I spent the time on it. I made it. I'm proud of it, but I recognize it might microwave your brain a bit. It's fun for people that have seen it before. When it's the first time, I know derivations are a lot. So, okay, great. This is the base definition, though. Energy per second per area. We need to get this in terms of electric field and magnetic field. That's kind of the motivator here. Electric fields and magnetic fields carry energy with them. That's the whole point of them. They carry information, specifically in the form of energy. They transmit that energy. When you all stand outside in the sun, you feel warm. Why? Because the sunlight carries energy, and it hits you, and it warms you up, and you have received that energy. That energy got converted from an electromagnetic wave to thermal energy. Solar panels. What are they doing? They're taking the electromagnetic energy from the sun and converting it into electrical energy. Now, to derive this, we're actually going to find the energy in the electric field, to find the energy in the magnetic field, we're going to use devices that we've learned before. We're going to use the energy stored in a capacitor for electric fields. Why? Because what does a capacitor do? It has a constant electric field in it. The energy in a capacitor, you could actually think about being stored in the field, not the charge stored on it, which is kind of weird, but it works. In the case of a solenoid, when there's a current running through it, the energy is stored in the field. And again, it's a weird idea that these fields store energy, but they do, and I'll let you chew it on. You can chew on that for a while. All right. Again, normally this is where I would start here and derive the whole thing, but for the sake of time, I'm just going to kind of hit you with it real quick. So this is the energy stored in a capacitor. This is something you should probably know for the test, for the final. This is one of the equations on the formula sheet, 1/2Q times V. Where does it come from? Feel free to look back, find that out. But we derived this forever ago. Okay. This equals 1/2 CV squared. Why? Because C equals Q over V in algebra. V equals this. This is the definition for voltage and electric field. This is the definition of capacitance. You put them in there and you do algebra. That's all that's going on here. We just take these equations, chuck them inside of each other, do a bunch of algebra, and we get that the energy is 1/2 epsilon naught E squared A times D. And if you want the energy density, the energy per volume, divide by volume. What's volume? Area times distance is the volume of a cube. So great. Just divide by that. It gets rid of it. Yay! We got the energy density. On to magnetic fields. These store energy. How? 1/2 Li squared. We derived this previously. The inductance of a solenoid is given by this equation. These first equations are ones that should be familiar to you. These are ones we've used. This is the inductance, and this is the magnetic field made by a solenoid. Rearrange them, chuck them in there, do some algebra. You get that the energy stored in the magnetic field is B squared over 2 mu naught A times L. A times L is volume. If you want the energy per volume, just get rid of that. Great. We have derived the energy stored in both fields. Electric field, 1/2 epsilon naught E squared AD. 1/2 magnetic field, 1/2 B squared over mu naught A times D. We add them together to get the total energy. Then we do some math. D equals velocity times time. Plug that in there. Power is the derivative. Put that in there. The DTs cancel. Yay. And ta-da, we got the power. That's the energy per second. Boom, there it is. What's the intensity? Take that and divide it by area. And there's the final result. We got there. A lot of algebra. It's nothing that... Every single step in here is just algebra. That's why it's stuff you all can do using equations from your formula sheet. So it's cool to kind of see this in my opinion, but it is a little bit of a lot. If you want the average power, we need to take the integral. It's a very easy integral. You just put the electric field equation, do an integral. Yeah, great. There it is. It spits out a 1/2. That's kind of all it does. All right. And why does it spit out a 1/2? This is something that's kind of used for you all. The average of a sine function over some time is going to be 1/2. And I keep putting this 1 here. I'll fix it later. All right. This is the equation on the formula sheet. Intensity. What is the intensity? What is the energy delivered per second per area by light? It's the amplitude of the electric field times the amplitude of the magnetic field divided by 2 mu naught. You can express it purely in terms of E. You can express it purely in terms of B if you want. Pick whatever you have. We care how much energy is being delivered per second. We care how much energy is being delivered per meter squared. The bigger the solar panel, the more energy you can capture. Makes sense. You get more sunlight. That's the idea here. This light radiates in all directions, so we care it's spread out among the whole cross-sectional area. And this is kind of a wild... When you think of how powerful the sun is, this maybe gives you some perspective. You all go outside and you feel warm from a sun that is so far away that it takes the light 8 minutes to reach you. The energy from that sun is spread on a sphere with a radius of how far away the Earth is from the sun. So the tiny cross-sectional, the tiny amount of area your body represents. So, here's the sun. Here's the Earth. The energy from the sun spreads out in a complete circle. It's spread out, a sphere. It's even bigger than a circle. It's a sphere. It is spread out uniformly on that. The percentage of area that you take up on that sphere is like almost nothing. And yet, the amount of energy is still enough to burn you. It is wild how much energy the sun is outputting. The fact that you feel warm when you make up like 0.000000001% of the intensity, the energy from the sun, that's what you're receiving, and it's enough to still burn. It's wild. Suns are big old energy factories. It's wild. All right. So on a smaller scale, I think this is kind of a cool problem. Notice it's number 15. We're nearing the end. There's only like 22 questions. A 2.5 meter diameter university, I don't know why it says university, communication satellite dish receives TV signals that have a maximum electric field strength for one channel of 7.5 microvolts per meter. It's very small, but we can measure it. Electronics are very sensitive. What is the intensity of this wave? What is the power received by the antenna? If the orbiting satellite broadcasts uniformly over the entire North America, how much total power does it radiate such that this amount hits the satellite dish? All right, try it out. Oh no.
That's what we use. That's that many miles. What did you want? Gotcha.
That's so big. That's good. I want to see what percentage we take up with that.
Oh.
Yeah. We're just gonna call it 1.5.
Yeah.
Squared. And then how much area? Maybe I should make a problem on this. This could be a fun problem. Let's do it like this.
I don't know. They probably do some more problem like this at Astro.
And how much energy it radiates? Alright, how much area should I take? I'm about 1.5 meters tall. By I think it's 1/2 meter.
Maybe less.
No.
They moved.
Oh. It did move.
Roughly.
Like, yeah, 40.
I'll just say 4, yeah. Do you know how to keep reference? So this is the intensity.
Yeah.
I just figured actually out that.
I'm like 0.3 meters. Or 0.4. Don't worry, I wasn't taking that into insult to my body size. I was like, there's no way that's 1/2 meter. We'll call it 0.35 or something.
True physics, because a human is a rectangle.
Oh, 100%. That's why I was doing this. It is roughly. You could smush it to a rectangle. So 0.525 divided by 2.83 times 10 to the 23. All right. I'll do it at the end of this problem. I'll put the answers up there too, because they're not going to give anything away. Something that's really fun is you may be like, wow, this thing's transmitting across the entire United States. That must require a lot of power. It's like 5 watts. And that's powerful enough to transmit a signal to the entire United States, no matter where you are. Because electronics are really sensitive.
How does the
Oh, I was being generous. It's 1.12 watts.
This one? I don't know how to use the area though.
All right, if you are stumped, remember, start with what am I solving for in part A? Always start with the objective. What am I solving for in part A? Intensity. All right, go to the slide on intensity. Boom. It's going to be one of those equations. It's the only ones I've given you. We're solving for I. Now you check, what do I have? If you're stumped, remember, this is the process for everything, any problem you ever have in class. First step, what am I doing? And you better write it shorthand. Intensity equals question mark, because if you don't know the variable for intensity, you cannot find the equation for it. If you cannot translate it into variable form, you can't use the equations. So, boom, do that, then identify the equations, which one's usable based on what I have. So look at what you have in the problem. That's going to help you identify what to use to solve this. This is a problem that is not super complicated.
Just to double check, do we always assume that we're looking for average intensity?
That's a great question, yes. A student asked a great question. Do we always assume it's average intensity? Yes. If I say intensity, if I didn't put the word average in front of it, assume I did. Pretend I did. I really should have put the word average intensity in it, but almost all the time when we talk about intensity, it's always average. A bunch of equations.
Oh, right, because we have the. I can't read.
It's okay.
So what we're going to do is decide which one to use. We're going to have to look at what we got. What variable was That's enough. We have the radius of the satellite. So if I want intensity, which is only that's enough. Yeah. The epsilon has 8.854 comes to minus 12. See, they're both constant. So we'll just plug them in and solve. Don't forget to convert your units.
No. You're welcome.
See, but I was just checking if you do that. Because your unit is watts per meter squared. And so that's what we're doing.
And this is like a semi-realistic problem. Satellites can't output that much power. They don't have that much energy to use. So like, These signals do not have to be that strong. When you do part B, what am I solving for? Oh, if only I had an equation that relates that. There's only one equation for it. They're solving for power.
No, not the store. The waiter.
You just look at this last slide and look where power shows up. And then choose the expression that you can actually solve. We do not know the energy per second. We can't use du dt. We do not have the energy to function of time. So power, intensity is power over area. You got the intensity. You got the area, or you can get the area. It comes from the definition. So this will let you find how much energy per second is received by the antenna. The bigger your radio dish, the more you can gather. This is why the bigger our telescope, the more data we can gather. The bigger your solar panel, the more energy you can get from it. Numbers.
Yeah, I was so upset about it too.
All right. So great. There's part B. Part C, it's the same thing, but you know. So how much power does it radiate if we use the entire area? It's just the same equation, but just use the area of the entire, area total. So if you want the total power that the satellite uses, then you're going to use the total area that it radiates over. So this is fairly straightforward. E to the minus 14 times the area of the US, 1.5 times 10 to the 13, and you spit out the 1.12 watts. All right. Yay. Just for fun, I did the calculation of how much area. So, great. There's the answers. What I'm about to say has nothing to do with these, but it's a fun little thing. So I mentioned you all, the sun is radiating power outwardly. It's radiating energy outwardly. The farther away you get of it, that energy gets spread out. So if we drew a quick picture of this, and I kind of drew it quickly, but I did some math. So here's the sun. Here's the earth. So at the earth, if we imagine a sphere, it's a terrible sphere. So the sun's energy is spread out among that entire sphere. The farther away you get, the more energy that's spread out. I calculated what this area was of the sphere. This radius, the radius of the earth from the sun, was 1.5 times 10 to the 11 meters. If you divide that by the speed of light, you get the time it takes for the light to reach here. Why do I mention this? So the total area of this entire sphere, all the energy from the sun spreads out in this entire sphere. So this is going to be 4 pi r squared. That's the area of a sphere. So this equals 4 times pi times 1.5 e to the 11 squared. So this equals an area of 2.8 times 10 to the 23rd meter squared. That's a really big area. That is 2 followed, move that decimal place 23 times to the right, and that's the area of it. I then calculated how much area I take up. Area of people. And in the classic physicist way, how did I calculate that? I pretended I was a rectangle. So, I'm approximately a rectangle. I'm about 1 meter tall, and I'm about 0.35 meters wide. And so this comes out to 0.525 meters squared. Thank you. So if I do the area of myself over the area total, I'm going to get the percentage of area I take up from this sphere that's, it's a huge sphere. And it is 1.86 times 10 to the minus 24. That's the ratio. That is the percent. That's the amount that I take up of this area. So if I wrote this out, 0.000, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. All right. That's how much space I take up, and yet the sunlight is still bright enough out there to burn me and give me cancer and all that fun stuff. If you want to know the total energy of the sun, if I could measure the energy that my body receives per second, and I multiply it by the inverse of that number, that's how much energy the sun's outputting every second. Which is nuts. Which is absolutely wild. I'm sure y'all have heard like the whole Dyson sphere thing. It's one of those, if we became a type 2, 3, type 1? Yeah, we're not even a type 1 yet. If we became a type 1 civilization, one of the hallmarks of that is how much energy you can get from the sun. And the Dyson sphere is if you completely surrounded it with quote unquote solar panels, you'd get all its energy, and it's such a stupid number that it's stupid. Anywho, all that to say, the sun outputs a lot of energy. That's my final remark there. All right. Let's see. How much more do we have here? Okay. I'm going to go very briefly on this. We'll do this reflection. I'm going to give you all a break, but I really don't actually plan on going too much further because we're nearing the end of what I wanted to get to anyway. So we'll still finish way before half the time next time. So I'm just going to go through this real quick. There's the electromagnetic spectrum. I'm not going to test you on it. What is the electromagnetic spectrum? It is all electromagnetic waves are light. All of them. Your Wi-Fi signals, the light you can see, X-rays, gamma rays, they are all the exact same thing. It's just how stretched or squished that wave is. The only difference between visible light and gamma rays that give you cancer is whether or not that wave is really squished or really stretched. That's it. It's kind of a wild idea. The only difference between the radio signals you pick up and gamma rays, again, are how squished they are. So this is the spectrum. It shows them all very nicely. You all can only see, your eyes have little sensors in them. Just like your cameras have sensors in them, so does your eyeball. Your eyeball has sensors in it that's some of it's sensitive to about 5, there's red, blue, green cones. And they're just sensitive to different wavelengths. They just respond. It's chemicals. It's, I don't even know what to call them. There are things in your eyes that are very sensitive to specific wavelengths. Why are they sensitive to those wavelengths? No idea. That's a biology question. An infrared camera is just a camera with sensors that are sensitive to the wavelength in the infrared. An ultraviolet camera is just sensitive, whatever the camera might be. You can see these things if you have sensors that are sensitive to them. Our human bodies can see only a tiny, tiny window of this, and that's fine. It's probably a good thing. If you could see all these, you would be seeing nothing. Because there'd be so much information right now going through your eyeballs that if you all could see all the Wi-Fi signals, oh my gosh, I don't even know. Hot mess. Real quick, as wavelength goes up, frequency goes down. Also, as you get to a smaller wavelength, you get more energy. We're not going to really get into that too much. You have to talk about photons. There's a relationship for it, but this is something you know. X-rays are more dangerous than visible light. Gamma rays are the worst. These are all arbitrary. Why is a radio wave? How do you define a radio wave? Someone at some point said radio waves are this big. Microwaves are this big. This is not something written in stone. We just split it up because that's what humans do. We categorize. All right. We'll talk about bouncing light, and then we'll save the bending light to next time because this is so easy to explain. Light acts like a bouncy ball. If y'all are cool with how a bouncy ball bounces, then that's what light does. So if I got a surface and I threw a bouncy ball down to the right, which way is it going to bounce? Wow, so will light. It's great. Super easy. This super simple idea, though, can help you understand lots of things. We're going to be treating it as a... I spelled effect wrong. We're going to be treating it as a ray because it's easier to draw than a wave, but I'm going to show you a sweet animation. Well, okay, I'm not going to. It's a video, but there's a cool video to see it. All right, so light will reflect off the surface at some angle. It acts like a bouncy ball. If the surface is smooth, then all the light bounces the same way, and you get a nice reflection. When the surface is not smooth, it's like trying to bounce a bouncy ball on a gravel road. It's unpredictable. It's going to go all over the place. You don't get a nice image. This is why shiny things are shiny. The light all bounces the same way. This is why not shiny things aren't shiny, because the light gets scattered. Again, imagine bouncing a bunch of bouncy balls on a flat floor. They're roughly going to all do the same thing. Gravel floor, chaos. Light does the same thing. This is a video from Khan Academy, so it's fine. I'm only going to show the first part of this video because it's cool, and I am doing a video right now, which is kind of weird.
Now,
remember that light is a wave, and every time, so here's my wave front coming in. Each of these are kind of the waves. And what happens here, you'll see the reflection in a second,
and now
a nice
common tangent
oh,
to
look,
all
there's
these
the
reflected
wavefront.
waves represent
So it bounces
the
at the same
reflected
angle. So it's a
wavefront.
nice little thing showing.
So let's see if we can really prove
light is
that
a
the
wave,
reflected
and you can
wavefront.
treat it like a bunch of infinite point sources. Yay. Great. Okay. I believe in you. If light hits a mirror at a 30-degree angle, which way is it going to reflect? Yeah, great question. I didn't say 30 degrees of what, and I should have. Whenever we're measuring this angle, something I'm going to teach you all is all these angles are measured with respect to the area vector. It's so nice teaching a calculus-based class, and I can use the word area vector. This area vector is the vector, so it's measured from that. So if this is 30 degrees, we always measure the angle with respect to this area vector. Great question. Thank you for asking. The next angle that you're going to measure will also be measured from the area vector, from that dotted line. Whatever answer you give me is from the dotted line. All angles are measured with respect to the area vector. Draw it. It's a bouncy ball. None of these So 60. So your picture here is off. So we're measuring. That's not 60 degrees. This would be 60 degrees. But visually, if you just look at your picture, this angle sure look a lot similar.
Yeah.
That's because they are the same.
I mean, that's like.
So right now, I haven't taught you anything other than light bouncing and bouncy ball. So your picture is awesome. It's exactly what it is. So I'm not really this picture, right? So this is the same. Because they are the same. So that's the rule. That's the rule of reflection. Light bounces at the same angle it hits with. And you can imagine if I... Yeah, it's very convenient. If I do it like at a super steep angle, then it's going to bounce. And again, you get the same. So you can imagine use your vast knowledge of bouncing balls on surfaces, and it follows all those rules.
What do you mean?
Yeah, but you bounced a ball like yeah. Yeah. I don't move. I don't play with anything ever. Alright, give y'all about 20 more seconds. I'm really leaning on your prior experience in life and that you bounced some balls off of the ground. Alright, 3, 2, 1. So, if this is a bouncy ball, which way is it going to bounce? You all, again, I say bouncy ball, basketball, I don't care what it is. You know that it's going to do that, hopefully. Hopefully you've had enough real-world experiences to see that. Oh, it's the same angle. Why? Because they look like the same. Because they are the same. This is just a rule. This is what they do. They always bounce at the same angle they hit with. You can see it from the picture. And if I didn't give you numbers, you probably would have been cool with that picture. Then you just have to see, oh, they look the same. Because they are the same. Ta-da! That's the law of reflection, which I didn't write anywhere. Oh, well. All right. What makes things shiny? Other things dull. Already talked about that. Gravel road versus smooth road. How do you make something really shiny? Make it really smooth so that all the light bounces the same way. How do you make something not shiny? Scuff it with sandpaper. Make some grooves and some divots. So why does it bounce all crazy? Because look at those area vectors. They're all over the place. The light's all coming in the same, but here's this area vector, here's this area. It's still following the rule that it's always bouncing the same angle, but my area vector is changing throughout the surface. That's the idea here. The light's all coming in. If you all look at this, all the light's coming down to the right. But the area vector is the one that's changing. So great. All right. Now we're going to do a couple fun facts. I'm not going to test you on this, but it's a really fun question. If I'm 3 meters tall, what's the smallest flat mirror I need to see my entire body? Drawing a picture is how I'm going to explain this, so drawing a picture might help you answer this.
Wait, like the light reflecting?
It doesn't see your eyes. Yeah. Huh?
Like, because when you stand in front of a mirror, you can't.
Oh, it doesn't matter how far away you
And
stand.
you can see your shoes.
Yeah, it doesn't matter. That's cool.
Theoretically.
It doesn't matter where you stand. This is the rule. And this is a flat mirror. If it's a curved mirror, your life is easier. Draw it.
Draw it.
Draw it.
But if you have a mirror and you can't see your shoes, you step back and then you're far enough away.
If it's a curved mirror, you can see it's a flat mirror.
It's like all these things are that way. And 45 degrees.
Draw it based on the idea that the light has to go from your shoes to your eyeballs. That's for you to see them. That has to happen.
Yeah, it's just
So you have to draw it out.
back of geometry.
Yeah, I think it's probably
The key here is the light has to go from your feet to your eyeballs. That is the key. So draw it. Draw the light rays going from your feet, hitting the mirror, bouncing your eyes. Remember the law of reflection. Angle in equals angle out.
Like, you know, like, I'll see you down. Really? Yeah.
No, I think it's gotta go anywhere.
Yeah, I don't know a good like mathematical.
Oh, I have no clue.
Other than just like geometry.
Yep, it's just. I think it's just a geometrical argument. I don't know. Maybe there's another way, but.
I mean, if you're far enough away in a telescope, yes.
And I am going to approximate my eyeballs at the top of my head.
Yeah, that's what I did.
We're going to approximate your eyeballs as existing on the top of your head. It's fine. It's roughly there. All right, 5 more seconds. 4, 3, 2, 1. Alright, so let's draw a bunch of light rays from our feet and show where they're going to end up. They're going to, every part of your body, if you see it, that means light from that. So light comes from the light source, hits your feet, and then it goes off of your feet, and then eventually gets to your eyes. That's how you see anything. Light has to come from the light source, hit something, bounce to your eyes. Your eyes are the sensors. If it doesn't reach your eyes, you do not see it. So, if I draw light from my feet, and let's say I draw it all the way up here, hit some random spot, it will bounce with the same angle. Clearly, that does not reach my eyeballs. So that's not the light ray that's going to reach my eyeballs. Okay? So if I go really low, that is also not going to hit my eyeballs. So where is the light ray? When you see your feet in a mirror, where does it have to hit on that mirror to see it? The middle. The dead middle. Why? Because it's going to bounce off at a 45-degree angle, and, great. You can see it bounces like a bouncy ball. Let's draw now our knee. Where does our knee, where does the light ray for that need to hit? It needs to hit somewhere above that. Why? Because you can see the picture matches correctly. And then as you go up the body, it's going to keep hitting above the mirror. So what's the consequence of this? We only need that part of the mirror. We don't care about the bottom of the mirror. Maybe you're like, wait, what about the bottom of the mirror? Okay, great, let's take like this, my belly button. If that hit the bottom of the mirror, that's not going to get to my eyeball. The bottom of the mirror is useless. So the answer here is, how big of a mirror do you need? Half the size of your body. Any size mirror will not work. If you're like, but wait, what if I just have one this big? Great. You'll see your bottom part of your body, but your hand? That doesn't reach your eyeball. You need to see your entire body. Any size mirror will not work. You need the entire half. Now, if you're like, I've used smaller mirrors, they were curved. They have to be a curved mirror to spread out the light. Can I see myself? Let's see. Oh, that's a good question. I don't. It's too far. It's too weak. But no, I don't think so. If you're like, but my camera, how does that? It's a curved. There's lenses on here that curve it. Now, look, I drew this as an arbitrary distance. If you all spread this thing farther away, it doesn't change the laws of physics. I didn't put this at any special spot. If I move this farther away, the same rule applies. This was I didn't draw this in any special place. I picked a random thing. It's a crazy idea. You're like, oh, if it makes it small enough. No, you will not be able to see your entire body, even if it was infinitely far away. Obviously, there's other problems there. All right, last fun question for you. Again, not something I'm going to test on, but it's fun. So this light's going to bounce off of things. It's very useful to have devices that when light hits it, that light bounces directly backwards, always, no matter which way that light is shining. So this means if light is shining, for example, up to the right, it will return down to the left. If I have light that's traveling straight on, it will return dead on. If I have light that is coming down from the right, it will go back up to the left. It goes back the way it came. This would be a very useful device to have. Something that the light returns directly backwards. Maybe like, why would this be useful? Reflectors. When you all are on, what does a reflector do? When you all put a reflector on you, what's the point of it? It's so that if a car or something's coming, the light from the headlights bounces back to the person who's driving the car so they see you. Reflectors make the light bounce directly back the way it came. That's why no matter where that car is, that reflector looks really bright. Why? Because it literally just shines the headlight back at the person driving the car. Another use case of this is if you're out in the ocean, it is useful for other people to know where you are so they don't run into you, or in case anything happens to your boat. So it's very useful to have devices that ping signals back. You know, if they send out a radar ping, you actually want them to find you. So try to, well, I don't know, it gives it away. Spend about 30 seconds seeing if y'all can think of a solution to this. How can I design some quote-unquote mirror that makes light bounce back no matter which way it comes in? It's not a flat mirror. I mean, that's really easy to prove. If you all put a flat mirror here, it ain't going to bounce back. Bouncy balls don't do that. This is bad. I heard maybe a curved surface. Curved surfaces also will not do this. In fact, a curved surface might actually focus some of these. Depends how the curved surface, but no, it's not gonna. Curved surface won't work either. It's a fun puzzle, and it has a really easy solution. All right, the answer is a 90-degree corner. So let me kind of map one of these out, and you can see what I mean. Here's what a 90-degree corner will do. So if I have, this is my area vector, this is my area vector. So if I have light coming in like this, it's going to bounce the same angle. And then it's going to hit this one. And I didn't do the best job. You see it roughly goes back the way it came. It bounces off the two surfaces. This works with bouncy balls. And now gravity kind of gets in the way. But like if you all throw a bouncy ball like down at the ground and it hits the wall, it will bounce back the same way it was thrown. Now gravity pulls it down, so that kind of distorts the effect. These are called, wild phrase, corner reflectors. All the reflectors, the vast majority of them, are this. They're a bunch of 90-degree angle things. If you all ever look at them, if you look into them, you'll see that. On boats, if you all ever look at sailboats or things like that, they sometimes have these big metal things. You'd be like, how is that a reflector? It's not reflecting visible light. It's reflecting different types of light. So they're useful. You may be like, that's not very shiny. It is to other types of light, the kinds that you can't see, radar, things like that, radar. And then the top left picture is one on the moon. So one of the things they brought on the moon mission way back when is a corner reflector. And this is very useful because now on the Earth, we can point a light source at it, have it bounce directly back, and figure out very precisely how far away the moon is from us at any given time. It's useful to be able to kind of do that. So yeah, that's just a fun fact. I'm not going to test you on it, but it is a cool little thing. There is some other example, like the ones on the road, it's a corner reflector. There is some other use cases where what they actually do, if you're like, what about that clothing that's super shiny, but like, there's no corners in it. They do some clever things where they'll like embed glass beads inside a material. And I mentioned that the curve doesn't quite work. It kind of does work. It does work actually decently. It's just not as good as a corner. But yeah, those pieces of clothing that have that like reflective quality, they just have these kind of things embedded in them that the light does effectively act like that. Whatever. All right, that's good enough, y'all. Look at that. 10 slides. Nope, okay, it's more. It's fine. It's not that much. It's really simple. This last bit, we're going to be coasting. Just like this reflection stuff.